This video will cover the age of the Earth, the interior of the Earth, and the Earth's magnetic field. We do have a scientific method for determining the age of the Earth, and that would be through the use of radioactivity and the principles of half-life for radioactive isotopes. Rocks can be analyzed and measurements can be made of the abundance of different isotopes in the rock. Different radioactive isotopes have different half-lives, a characteristic lifetime. The half-life is the number of years or minutes or seconds required for half of the isotope to decay into some other isotope. So measurements are made and ratios are done for the different isotopes that are present. And the calculations would indicate that the rocks we see on the Earth are about 4 billion years old. It is presumed that the Earth was molten and original rocks don't exist, but only after the time the Earth cooled to form a crust. So probably the Earth is older than 4 billion years. And again, I don't have a conflict with this and the Bible. 2 Peter 3:8, one day with the Lord is like 1,000 years, and 1,000 years like a day. So we do have a scientific age for the Earth, about 4 billion years. As we study moon rocks and meteorites, some of those are older, coming from regions that did not have the molten characteristic to them, especially the meteorites, more of the old material in the solar system. So there's our scientific age for the Earth. An illustration here of the principle of half-life. We start with a certain number originally of isotopes. After one half-life, we're down to half the material. Another half-life, we're down to a quarter of the material. Another half-life, we're down to 1/8 of the material. And we get this curve for the abundance of a particular isotope with time. Uranium has some very long half-lives, 4.58 billion years, no, 4.5 billion years. And as the uranium decays, it produces other elements in this decay series, ending with the stable isotope of lead. But these other isotopes then can be measured and their abundance determined, and ratios can be made of the abundance, and the radioactive half-life can be found. What about the interior of the Earth? Is it hot or cold? Well, we have evidence that it's hot. We have volcanoes bringing up hot material from the interior of the Earth. Earthquake waves, there's a form of wave that will not pass through a liquid, and that indicates, as geologists study the earthquake waves, it indicates that there are regions inside the Earth that are molten, and that requires hot material. As you go down in a mine, or if you drill in a well, temperature measurements can be made, and the finding is that the temperature increases as you go beneath the crust of the Earth. Our deepest well is about 8 miles. Scientific study, not oil. And there's evidence that there are heavy elements in the core, iron and nickel. The overall density of the Earth is higher than the density of rocks that you just find in the crust of the Earth. So the way to get an overall density higher than what's on the crust is to have dense material in the core. That's the iron and the nickel. And the iron and the nickel fit in with this dynamo theory for production of the Earth's magnetic field, where we need electric currents inside the Earth, and the iron and the nickel provide that conducting material. It is believed that the Earth is differentiated, and all the terrestrial planets are differentiated. That means they have higher density in the core than on the crust. So young Earth was molten, not solid crust like we have now, but molten material. In a liquid, the dense elements sink to the middle. Gravity pulls, has more force on the dense material, so it pulls it towards the middle, and we get our iron and nickel in the core of the Earth. Not so much on the crust, although volcanic action can bring up heavier elements to the crust of the Earth. But differentiation gravity causes the heavier elements, the denser elements, to sink towards the middle. So we find by studying the gravity fields around terrestrial planets that they're all differentiated, and by studying their densities, we find they're differentiated. What's that imply about the history of all the terrestrial planets? Well, it implies they were all molten at one time, so that the heavy elements could sink to the bottom, sink to the middle of those planets. So evidence of hot interior, volcanoes, and many other places than just Costa Rica. Models of the temperature inside the Earth. So the depth of zero, the crust of the Earth, is way over on the left. And models show fairly substantial temperatures, certainly above the melting point for iron. So liquid core. Model of the core: as the pressure increases towards the center, the pressures can be high enough to make a solid, even though it's high temperature. And then we have the liquid outer core, where the electrical currents are thought to be existing to construct or to form the Earth's magnetic field. A mantle of rock material in our crust where we live. So, Earth's magnetic field. I've talked about magnetic fields for the planets before. Again, the model is we have electrical currents in the core, in the liquid core of the Earth, that produce the magnetic field. It's too hot for a bar magnet to exist inside the Earth, a permanent magnet. So electrical effect, creating a magnetic field. The Earth's magnetic field is stronger than the other terrestrial planets. It's not as strong as the Jovian planets, but we have the strongest magnetic field for the terrestrial planets. This magnetic field does apply force to charged particles, say from the sun, that are coming towards us, or cosmic rays, high energy charged particles from our galaxy. But we get protection from those. The magnetic field deflects the path of that solar wind and somewhat diverts it around the Earth, so it does not impinge on our atmosphere and cause a problem with sort of eroding our atmosphere. This electrical dynamo is the hypothesis. It is known that the Earth's magnetic field has changed directions, flipping North Pole and South Pole. As lava comes up on ocean ridges where new seafloor is forming between North America and Europe, for example, as those rocks cool, they carry with them the direction of the magnetic field when they cooled. And this direction changes as your distance away from the ocean ridge increases, where the rocks were formed more distant in the past of the Earth. There's not a set time, like clockwork, that the magnetic field reverses, but about 300,000 years is sort of an average time for a reversal, and we're due. So here's a graphic that illustrates what's happening here on the ocean ridge. Molten rock is coming up and forming new seafloor. As it cools, it locks in the direction of the magnetic field, and we get these stripes where today's direction of magnetic field is in the more darkly shaded, and in the white areas, a reversed magnetic field direction. So when this rock in this white band formed, the north and south poles were reversed compared to today, and then reversed here, then reversed here, then reversed here, etc. So this is an illustrative artwork, not exact data, but just shows you what happens. Okay, the Earth's magnetic field. Again, this protection device that we have, the solar wind pushes in on the magnetic field here, extends out the Earth's magnetic field back behind, and there's some interesting activity that can happen when there's sort of a superabundance of particles in the Earth's magnetic field. A solar storm would occur and supply us with more particles. Some of those will leak down into the poles and cause the aurora. We have the Van Allen radiation belts, discovered in the late 1950s by Dr. Van Allen, the University of Iowa. There's an inner belt that's mostly electrons and an outer belt that's mostly protons. Our astronauts are in low Earth orbit. They're inside these radiation belts. It is somewhat hazardous to spend lots of time in this volume of the Van Allen radiation belts. These radiations are damaging to biology, to biological life forms, and so our astronauts spend their time in low Earth orbit where the radiation is not as intense. Or if they have to go to the moon, then they travel through this region quickly so that they don't receive a big exposure. Aurora taking place as electrons come into the Earth's atmosphere, collide with atoms in our atmosphere, and make those atoms glow. And those are studied by sending balloons or rockets into the area, especially rockets. And we can observe the aurora from space, the International Space Station here, taking a photograph of the aurora from above. And we get these kind of sheets where the electrons are being guided by the Earth's magnetic field into the atmosphere of the Earth. So I hope you enjoyed a little tour there of age of the Earth, hot Earth interior, and magnetic field. You ought to write down some questions and ask them.